We have a very interesting related rates problem here in that we have a television camera positioned 4,000 feet from the base of a rocket launching pad. The angle of elevation in the camera has to be correct in order to at the correct rate in order to keep the rocket in sight. And we also have to take into account the increasing distance between the camera and the rocket to maintain the autofocus. So we're going to assume the rocket rises vertically. So first, let's just get our situation going. So here's our 4,000 feet. Maybe our rocket is here, and we're over at this point. And so that rocket is going to take off. So that little arrow will be our rocket. And so here's basically our situation. The 4,000 feet is static. The height of the rocket is something that's going to be changing. So let's call it h. Something else that'll be changing, the distance between us or the camera, and the rocket. Maybe let's call that r. And the other thing that'll be changing is the angle of elevation. So we've introduced our situation, we've introduced our variables, we can start to come up with relationships. In part B, what we're going to do is come up with a relationship between the angle of elevation, so the angle of elevation of the rocket, and the height of the rocket. Now if we look here, h is the opposite side, and we'll want to use 4,000 because it's static. We don't want to deal with more variables than we need to. So we got the opposite over adjacent side, so tangent theta equals opposite over adjacent, h over 4,000. And to make it a little simpler, let's go ahead and just solve this for theta using an inverse tangent. So an arctan, so tangent inverse of h over 4,000. Alright, now it also asks us to come up with a relationship between the rate the angle's changing and the rate the height is changing. So that means we're going to differentiate both sides with respect to time. So d theta dt, because the derivative of theta with respect to time is just d theta dt. Now we're going to have to do a chain rule. The outside function is an inverse tangent, or an arctan. Remember, the derivative of arctan is 1 over 1 plus whatever you're taking the arctan of. In this case, it's h over 4,000 times the derivative of the inside. So times the derivative of h over 4,000, so times 1 over 4,000 times the derivative of h with respect to time is dh dt. Alright. Oh, sorry. This is 1 over 1 plus what's inside the arctan squared. There should have been a squared there. My mistake. And so there's our relationship. It's not pretty, but we've got a relationship between the rate that the angle is changing and the rate that the height is changing. C asks us to do something similar, except now it wants us to come up with something for r here. Well, notice what we have is a right triangle. So r squared is equal to 4,000 squared plus h squared. Again, I think we could do the related rates problem like this, but let's go ahead and solve it for r. So r equals the square root of 4,000 squared plus h squared. And that's, since we're going to be taking the derivative of this, remember that this is 4,000 squared plus h squared to the 1/2. And yeah, we can multiply out the 4,000 squared. I'm just leaving it that way for right now. We'll need it later. So what we'll do now is we'll go ahead and take the derivative of each side with respect to time. So that just becomes dr dt. So just to mention it, if I had done it from here, that's not a problem. It's actually a very easy derivative, but r will still be in my related rates problem, which means I have to go back and find r at some point. Not a big issue. I just decided I want my dr dt to only be in terms of h. Now here, my derivative outside, I pull the 1/2 down, so 1/2 times 4,000 squared plus h squared to the negative 1/2, now times the derivative of the inside, which is 2h dh dt. Alright, and we can clean this up a little bit. For instance, these 2's will cancel, And so we're going to get dr dt is h over the square root of 4,000 squared plus h squared times dh dt. So we've set up our two related rates equations. Now we're ready to go do some work on these. So part D says, how fast do we need this angle of elevation changing at the moment that the rocket is 3,000 feet in the air? So that means we're looking for d theta dt when h equals 3,000 feet, and the height, and it says to assume that the rocket is going up at a constant rate of 600 feet per second. We have our formula. It is now just a matter of plugging in our values. So we're going to have 1 over 1 plus h is 3,000, so 3,000 over 4,000 squared times 1 over 4,000 times 600. What's really nice is since we identified these values, we really are just plugging into our formula. Evaluating this, we get that d theta dt, when all is said and done, comes out to be exactly 12 over 125, or if you want to do it as a decimal, 0.096. This is going to be in radians per second. Okay? We're in radians in this problem. If we wanted to, we can convert that. That actually comes out to about 5.5 degrees per second. If we wanted to have it in degrees, and just multiply by 180 over pi. Now, we also want to figure out how the distance is changing. This dr dt is going to be changing at various heights. Again, we're going to assume that the rocket's going up at 600 feet per second. So dh dt is still 600. Well, look at what happens. Because of the way the h's are, these are going to be pretty similar answers. So we're going to have a dh dt here, and now if h equals 3,000, dr dt, just calculating it from our model here, comes out to be about 600. It's going to come out to be 600 times our h's 3,000 over square root of 4,000 squared plus 3,000 squared. We'll calculate these in just a second. But let's go ahead and set them up. At 4,000 feet, our dr dt is going to be the 600, except in almost the same, except now we have 4,000 over the square root of 4,000 squared plus 4,000 squared. So let's get an estimate of these r so we can see which one is going to be greater. So if we calculate this, we have 600 times 3,000 divided by the square root of 4,000 squared plus 3,000 squared. Okay, so we get 360. So that is going to be equal to 360, and now our units on this, remember, we're looking at a dr dt is going to be in the same that we measured before, the dh dt, which is feet per second. Now at 4,000 feet, this is one of the nice features of the calculator, I can just do second entry and change my 3,000s to 4,000, and we see we get a little bit larger number at about 424.26 feet per second. Which, if we think about it, makes sense, because as the rocket gets further away, the rate that its distance is increasing from us is going to be increasing as well.